Started. Today we're actually starting our first metabolic pathway. We're going to do glycolysis. I don't know that we're going to get all the way through all 10 steps, or 10 steps for glycolysis. And unfortunately, there's no easy way to do this other than to memorize them. However, I want you to understand the rationale behind it. And so once again, one of the reasons why I've been pushing, knowing the enzyme classes and names, is you can learn a lot. And those in chemistry and cancer, we've been also reinforcing that idea. You can learn a lot about what kind of substrates and products it's made, what kind of reaction it is, just based off of its name, and vice versa. If you see something, then you can kind of narrow down and get a good idea, at least, of what kind of enzyme it does it. So I want you to know overall what happens in glycolysis, what you start off with in the full glycolysis, like the traditional one, what we start off with, and what the end product is, what the whole purpose is for glycolysis, which usually when I ask that question, people get it wrong. And so, and that's one of the reasons why I like to ask it, like whenever we do our discussion, but usually by the end of the semester, you guys understand that. The three possible fates of pyruvate, and then once again, you just need the 10 steps. I can't click on these animations because the Mac program doesn't let me do that, but I have 3 different animations. I haven't checked to see if the links work. Animation number 1 goes through all the steps, but it's very slow. If I remember, it used to take forever to upload. It was really nice. 2 is very simplified. And 3 gives the enzyme. You have to keep on clicking on each of it, and unless they changed it, the enzyme name to match up with it wasn't obvious, but it was best, most information. But there are lots of them out there, and you can now, more and more lectures and everything is available on YouTube. Okay, this is a glycolytic pathway, and ultimately, you get 2 pyruvate molecules for every 1 glucose that entered into the pathway. So that's why it shows you, this is a very simplified version. It came from the old book that I actually didn't care for this old book. It was more of a nursing biochemistry type of book. So it's very simplified, but it does give you an idea that we have a glucose, you make 2 pyruvate, and then there are 3 possible roles and places that pyruvate can go through. Once again, not all of the slides are in the handout that I gave you, but I get the high points and everything like that. And I won't always have them handed out for you, but since the class was small and I didn't get time to put this on my file beforehand, and it's so important, I wanted to make sure you guys had access to it for today. All right, but we start off with the glucose and we make 2 pyruvate. So this is the generic scheme in the sense that, I shouldn't say scheme, an idea that there are 10 enzyme-catalyzed reactions. And glucose, which is a hexose, so if you think back to last semester, meaning it's got 6 carbons and it's a sugar, is converted to pyruvate. Pyruvate is called a keto acid. If you think back to organic chemistry 2, it's a keto acid because we have the ketone on the carboxylic acid, carboxylate. Okay, so this one, by the way, is called an alpha keto acid because it's not drawn all the way out. Let me draw it all the way out. Let me change this too. Oh, no, I think it's still, there we go. So pyruvate, we have a methyl group. You're going to know, I don't tell you, memorize the structure of pyruvate, but by the end of the semester, you're going to know it. Okay, and there's a reason why. There's a methyl group, the ketone, and then the carboxylic acid, carboxylate. And that's why it's called alpha, because we have the ground 0 carbon, and then alpha next door to it's the ketone. And the reason why I want to point that out is later on when we talk about fats, beta keto acids are really important for fats. But here, pyruvate is called an alpha keto acid. But we start off, we have glucose, we have pyruvate. Overall, there's a net conversion of 2 ADPs to make 2 ATPs. So once you have pyruvate, there are 3 possible fates. I think this is the one that's boxed on yours. And it depends on the organism and the conditions with which the pyruvate is synthesized or the conditions that your body or the organism is in at the time. So first, I'm going to talk about humans, okay? And for us, pyruvate only has 2 possible fates. I see that with a little asterisk. For normal humans, pyruvate only has 2 possible fates. There's under aerobic conditions, which what does it mean if it's aerobic? oxygen. So if there's oxygen around, then it goes on to make carbon dioxide. Okay, so it's going to go through a citric acid cycle. That's not shown here, citric acid cycle, and all the metabolic pathways from there on out. Under anaerobic conditions, which primarily occurs in your muscles, then what's going to happen is there's not enough time for the oxygen, and so your oxygen becomes depleted, and it's going to go on to form lactate. Okay. Which, if you notice, the only difference between pyruvate and lactate is the reduction that happens at the ketone, at the alpha position. So it goes from a ketone to an alcohol. And we'll talk about the reason why that's important and what roles that plays later on in metabolic pathways. Then the third way happens in yeast and some other organisms that under anaerobic conditions, they can do fermentation, and they go from pyruvate all the way down to alcohol, to ethanol. Of course, brewers utilize this in order to make alcohol. I always state, and I actually have a blog post from some time back, I state normal conditions, these are the only two ways that humans utilize. And the reason why is it's actually in the literature, and it's a kind of a funny story. And I wouldn't say the man was a Southern Baptist man, but he actually was hospitalized for alcohol intoxication, like alcohol poisoning and all this kind of stuff. And he kept telling people he didn't drink and all this kind of, this. And they kept saying, that he was an alcoholic. And come to find out, lo and behold, he had, such a yeast infection, like a symbiotic relationship in his gut, that he did ferment. And so he fermented sugars down to alcohol. Of course, then you can try to work on the microbiota, the flora there, in order to get rid of that. So that's why I say it's very, very rare, but in theory it can happen. That, once again, it's not the human himself, but it was the organisms that reside within the gut that could do that. All right, we're going to actually start in the beginning. So we have the first reaction. We have glucose, our good friend glucose. I do not make you memorize the structure per se. What I want you to do is, many times, it's sort of like this, where something, at least one or two things will be missing, and you have to fill in what's missing. I may give you the enzyme and the product, and you have to figure out what the substrate was, or vice versa, or like this one. Or maybe you're missing something else, like the cofactors or something like that, where you just have to figure out. I actually had to write it out back whenever I took Biochemistry 1, which we did glycolysis very first week of Biochemistry 1, way back then. We had to do electron pushing. In the proposed electron pushing, all by hand for all 10 seconds. I mean, it was horrendous. Absolutely horrendous. And I'd only had organic chemistry 1. I hadn't had organic chemistry 2 yet. So it was scary. In fact, a couple of my friends that had an apartment together, what they did is they had an entire wall that was nothing but glycolysis and electron pushing and all that kind of stuff that we wrote all over it and that we used. I'm sure the landlord loved that. Okay, but this is the very first step. And so, sometimes I even, just because we can go back and forth. We start off with the glucose. We make glucose 6-phosphate. It utilizes an ATP to put on a phosphate, and there's ADP that's kicked off. Okay. Once again, this is showing it as one step, as what we've already learned in the previous chapter is, in reality, if you looked at the enzyme mechanism, there could be two separate steps, but it doesn't leave the enzyme, so it's not transient. I should say it is transient. It's not, in the sense that it doesn't, I can't think of the word I'm looking for, where it doesn't completely leave the enzyme to go out and have to rebind. Okay. So what class or classes of enzymes can perform this? This is a kinase. See, that's why I say knowing is half the battle. G.I. Joe from the 1980s. But we have to now think about what type of kinase this is. Sometimes it's named after the substrate. Most of the time it's named after the substrate. Sometimes it's named after the product. Sometimes it's named after the class of compounds. Okay, and especially those that are named after the class of compounds usually indicate that they're more promiscuous. Okay, so what are some of the possibilities here? Glucose kinase, or sometimes they like to abbreviate glucokinase or something. All right. You can maybe say glucose 6 kinase. What broad class of compounds is glucose? It's a sugar, but what kind of sugar? And it's an ose. Someone said it. Hexose. And that's what this one is. Okay, this is hexokinase. All right. So this good old friend hexokinase. And remember one of the little tidbit I told you to just know, when we're moving phosphates around, just stick a magnesium up there. This one does require magnesium. Without it, it doesn't work. It's not efficient enough, okay? We're going to see hexokinase over and over again because the fact is that it is more promiscuous. This one you have to be kind of careful because you say glucokinase or glucose kinase, that's kind of like a little caveat. We're going to actually, there is a glucokinase or glucose kinase that's specific, but it's specific for one tissue, or actually specific for two tissues, and it has a specific job, and it does differentiate between hexokinase. But yeah, in general, for most cells, we're talking about just good old hexokinase. You do not need to memorize the numbers and everything, but what we can see here is that it's driven, it would be energetically unfavorable, like just to take inorganic phosphate and stick it on the glucose, it would actually require energy. But what happens is by first phosphorylating the intermediate, we get to capitalize, economy, fiduciary integration instead of faith integration. We get to capitalize on the fact that the hydrolysis of ATP is so profitable, so to speak, that overall it's a negative 16.7. Okay, but once again, don't memorize the numbers. We're just going to know that we're going to talk about anytime there's something special about this, about an enzyme, you should know it. Okay, and so I'm going to put a little asterisk next to that one. So that's step 1. This is step 2. Step 2 utilizes our glucose 6-phosphate and transforms it into fructose 6-phosphate. Okay. So if we look at the difference, I forgot to point this out, but kind of the name hexose kind of implies, but how many carbons are there in glucose? 6. And how many are in fructose?
5.
No, in the entire compound there are 6. There's 1, 2, 3, 4, 5, 6. So how are glucose and fructose related? Because we didn't get rid of any carbons. We actually didn't get rid of any functional groups at all. They're isomers. It's given up right here. So this is an isomerization. It's just the linkage that's changed. It went from being a pyranose, if you think back to last semester, which means it was 6-membered rings, to a furanose, which is a 5-membered ring. Okay, so this is fructose 6-phosphate. By the way, we're going to see some of these, both glucose 6-phosphate and fructose 6-phosphate, are involved in other metabolic pathways, but this is just our first one. So you're going to find out, just that one chart that I tried to show you, and if you look back on the older slide, whenever you get a chance to look at it on your own, many of these metabolic pathways will intersect with each other and have common points. It kind of reminds me of like a really, really large city that has a large mass transit system, where the common points intersect. All right, so what classes of enzymes can do isomerization?
Isomerase.
Okay, and so this is an isomerase reaction. So now, what kind of isomerase is this one? So this one's actually got 2 acceptable names, and I'll take either one, okay? What it is called phosphohexose isomerase or phosphoglucose isomerase. Probably more people will be called phosphohexose. In the sense that, it's promiscuous. Both these are hexoses, because they both have 6, but it does require that they have to be phosphorylated. Okay, and so a lot of times I'm going to even abbreviate my... Okay. Once again, or I could have covered up the glucose 6-phosphate and shown you the name and the product or something like that, and I would expect you to figure out, okay, this is the substrate that started, or would give knowing the product. And sometimes they even like to abbreviate, or I may even abbreviate later on, You know, we start off with this one was glucose, becomes glucose 6-phosphate. This one's glucose 6-phosphate. Whoops, it's supposed to be in a circle. Glucose 6-phosphate becomes fructose 6. Oh, I did it again. Okay, but you get the idea that sometimes you'll see them abbreviated. And you can abbreviate it as long as you explain what the abbreviation is somewhere if you're writing a lot. This is the third step. Now we're taking, just let me make this smaller. Fructose 6-phosphate to make fructose 1,6-bisphosphate. What's one thing, if you just look at it, what's one observation that you can make? It's what? It's adding phosphate group. It uses ATP. What else can we say? What's something that actually is easy to overlook here? I forgot to point it out in number 1. I put the asterisk, and this is another asterisk. But wasn't true for like number 2.
Magnesium?
Oh, this one does require magnesium. What else is something else that's there? Well, I mean, it does. They have a different phosphorylation charge. No, this is like even so simple that people just overlook it. That I forgot to point it out. I forgot to point it out in step number 1. Look at the arrow. What's important about this arrow? It's irreversible. And the same thing was on number 1. I put the asterisk. I'm trying to tell you why I put the asterisk. So step number 1 is essentially irreversible, okay, because of the hydrolysis of ATP. This one's irreversible. We have a hydrolysis of ATP. So what class or classes of enzymes can do this? Say it with some kinase. By the way, this is one of my favorite enzyme names. So if you were to name this kinase, what would you name it? Because what do both of these compounds have in common? They're both fructose, and they both have phosphates in it, okay? This one is phosphofructokinase. Just sounds like, for whatever reason, reminds me of Roscoe Pico train from Dukes of Hazzard. And technically, this one's PFK1, and it's fine to abbreviate this one PFK1. All right, and if you had just said phosphofructokinase or PFK, that's fine, but yes. Phosphofructokinase 1. And then there are importance because tissues utilize PFK1. There are certain times that we're going to talk about, like PFK2, and what the importance of PFK2 is versus PFK1 later.
It's fine because it's setting the phosphorylation.
Well, no, because this one is called PFK1 because it's the first isoform, first isostate. Because there is a PFK2.
And it's unique because it's irreversible.
It's irreversible, and I'm going to point that out. This one is one of the main regulatory steps in glycolysis. There are 3. We've covered 2 of them so far. Regulatory step first one is hexokinase. It's irreversible, and so we'll talk about how it's regulated. Actually, technically, that's next chapter. I don't know why they put regulation in a completely separate chapter, but it's irreversible. Second, like a checkpoint, so to speak, is PFK1. Okay, and this tells you a little bit about it. PFK1, like I said, is key regulatory enzyme. It's technically a tetramer, and it's subject to allosteric feedback. Where have we seen allosteric before? What's one example from last semester? Hemoglobin. Of course, hemoglobin is positive cooperativity. This one can actually be negative because that's just feedback inhibition. So the M isoform is called is M for muscle and L is for liver, but you can have all varieties of these mixtures together from M4 to L4, and they just have slightly differences in how that they are regulated. Okay, so that way some of them are going to be more active than others, or some of them will be more active under certain conditions or inhibited under certain conditions versus others. Okay. ATP, and I want you to understand the reason why this makes sense. Why does it make sense that ATP would inhibit this enzyme? We go over the inhibition stuff a lot of times later on, but this is a good review for the next chapter. Why does it make sense that ATP would inhibit it? When does glycolysis kick in? When do we need to use glycolysis? When we're low on energy. So what's one indicator when you have lots of energy? We already have lots of ATP, so if the ATP gets too high, it's going to downregulate and inhibit this enzyme. So therefore, it turns off glycolysis. So it's not a futile cycle. Okay, so it won't keep on going. As long as you're healthy, it won't keep on going because it knows that we need to store our resources for those times. Of course, Western diet is a little skewed, but during those times whenever we would be lower on energy.
So like a negative feedback?
Pardon?
Would be considered like a negative feedback?
Right, this is negative. It's our feedback inhibition. Because remember, overall, 2 ATPs get made. So far, if you notice, we've used up 2 ATPs, just like another fiduciary integration, step-based integration. You know, they say it takes money to make money. It takes ATP here to make ATP. Right now, we've used 2 ATPs before we've made anything. Right. And then finally, fructose 1,6 bisphosphate is also an inhibitor, which should make sense because if we go back, which I can't because it'll scroll to the end, it's one of the products. Okay. This just shows you an example. We were just talking about in calculus and chemistry of cancer, how calculus is important. And I drew an example of this before, but this is just like what I've seen before. This is the initial velocity, the reaction velocity, as a function of the substrate. So it would be Michaelis-Menten. Whenever ATP is low, what's that shape called right there? It's hyperbolic. Whenever ATP is high, what's the shape become? What is that shape? Sigmoidal. And so what that means is now you have to get to really high concentrations of substrate if there's high ATP before you can get the reaction to occur. Okay. And so that's why it goes from being hyperbolic under low ATP conditions to becoming sigmoidal into high ATP. So that's how ATP inhibits it. And so at the same concentration of substrate, here, let me draw on it. So if we just look at this concentration substrate, we draw up under low ATP conditions, this would be the velocity. Under high ATP conditions, this would be the velocity. Now we're to reaction 4. We're going to see reaction, we're going to talk a little bit about reaction 4 and how it's important. Okay, and so notice it's got a little asterisk, but it's important for a different reason. It is not a checkpoint. So if we just look overall, what happens is we start with fructose 1,6 bisphosphate. We make 2 products now. So there's a cleavage reaction that occurs. One product is dihydroxyacetone phosphate, and one is glyceraldehyde 3-phosphate. So if you remember back to last semester, one thing that I suggested that you do, and this will help you, let me just make this smaller, is I usually tell you, don't sit and memorize things, but one thing that you can memorize is glycerol. How many carbons are in glycerol? 3. And what makes glycerol glycerol?
The alcohol group.
Right, there's 3 alcohol groups on each carbon. That's glycerol. So glyceraldehyde means that one of those alcohols becomes, my eraser was too big. One alcohol becomes an aldehyde. So it's oxidized. Okay? Remember, these actually have hydrogens hanging off of it. So that's glyceraldehyde. 3-phosphate just means, once again, if this is a ground 0 carbon, it's carbon 1, carbon 2, carbon 3, then what they do is, and I'm going to change it in a different color, this becomes a phosphate. So that's why, even though you don't have to necessarily sit there and memorize all the structures, if you know glycerol, and you work your way backwards, then you can actually, or forwards, I guess, I don't know, whatever direction you want to think, work your way towards it, you can figure out what glyceraldehyde 3-phosphate looks like. Dihydroxyacetone phosphate is very similar, because what is acetone? How many carbons are in acetone? Well, there are 3 total, because remember, it's from organic chemistry. This is acetone. It's kind of a misnomer. Acet usually means 2, but technically it's a carbon. There are 2 carbons that hang off of the ketone. And so dihydroxyacetone phosphate literally means dihydroxy. And then one of those becomes a phosphate. It doesn't really matter which one. So, I mean, that's it. But they also give this one, I like to think of it as a hip-hop street cred name. It's DHAP. Why say dihydroxyacetone phosphate every time? It's DHAP. We're going to see DHAP and glyceraldehyde 3-phosphate multiple times throughout this semester. It's one of the reasons why I've taken some time to work on it. So one other thing I want to point out here is the fact that we start off with 6 carbons and 1 substrate, but we ended up with 2 products, each of them with 3 carbons. So the reason why this one has an asterisk is it's almost like a choose your own adventure. Depending upon whether it's the DHAP or the glyceraldehyde 3-phosphate, one of these goes directly onto step 5. One of them goes directly onto step 6. Okay, so that's why there's that's why I have an asterisk there. So you have to realize that, and many times whenever I draw this later on, or sometimes whenever I draw it, I would write it out this way. You know, glucose 6-phosphate, fructose 6-phosphate. Of course, you can write in the enzyme names. And then we had fructose 1,6-bisphosphate. And then what happens here is you get 2. You get DHAP, and you get glyceraldehyde. 3-phosphate. Yes, 3-phosphate. Or whatever, however you want to abbreviate it. Glyceraldehyde 3-phosphate. So what we're going to find out is one of these, that's step 3, this is step 4. One of them actually gets to skip step 5, because step 5 is where you can convert between the 2. Okay, so you have to remember also that from step 6 on, this is a little side note to me when I swear, you have to multiply everything, I was going to say by 2. By 2, okay, because they only show one of them, but remember we had 2. We start off with 6 carbons, and then everything only has 3, because pyruvate only has 3 carbons in the end. All right. Oh, yes.
Sorry, you said DHAP is what goes on to step 5?
Oh, we're going to get there.
Oh, okay.
Yes. Oh, whoops. Okay, so this one's got a special name. Normally I would kind of tease people along and say, okay, what class of enzymes can do this? And they would talk about lyases and all this kind of stuff, and that could very well be right. But this one's got a historical name, so I'll just tell you. The name on this one's called aldolase, because it makes an aldol. Okay? Because what is an aldol? We don't really talk about it. It is an organic. So what's an enol? No, that's an organic compound that has what 2 kind of functional groups? Alkene and an alcohol, right? Enol. Well, an aldol just means that it's going to have an alcohol and what other kind of functional group? Aldehyde. And so see, it's got an aldehyde and an alcohol. So this is aldolase. Pardon?
That was part of my capstone.
Oh.
From last semester. Aldolase.
Okay. This is one of the mechanisms that I only want you to know, like a couple of mechanisms. There aren't too many, but one of the reasons why is I want to point out things that are important. So aldolase here, and this is the way biochemistry likes to do electron pushing versus organic chemistry. First of all, you'll see hydrogens pop on and off all the time because they just assume, hey, we're in an aqueous environment. So it means there's water around. So, or they'll just call things generic acids and bases. But what happens here is it has an important lysine. Of course, lysine can act as a nucleophile. Okay? And what it does is it bangs into, smacks that carbon of the carbonyl group. Boom. Sound effects optional. Something's got to break or give, so you break to form your tetrahedral intermediate. So nothing earth-shattering there. We've seen it over and over and over and over again in organic chemistry, and we'll see it over and over again in biochemistry. The reason why I want to point this out is they give this one a special name. This lysine acts as a shift base. It's called a shift base is because it's going to form an imine. See right down here, it's forming an imine. Because what happens is a general base next to it or near it comes and it swipes one of the hydrogens off of that lysine, so those electrons can then go to form a double bond. Something's got to break or give once again, and what breaks is the oxygen will leave as a water. See, this is where they just say, hey, look, there's hydrogens around. That's just, it's kind of like their fudge factor, okay? Because usually it's an activated water or something that's nearby. So there's water left. So we form the shift base because it's an imine. Then on the other side of the enzyme, we have a generic base that comes, takes the hydrogen, pushes down to make a double bond. So boom, boom. Something's got to break or give, and what breaks, and this is the reason why these shift bases are so important, is we can actually break, it's hard to break a carbon-carbon bond, but whenever it's next door to a shift base, it's easy because this bond can break to form a new double bond, because this bond here can break to go to the nitrogen. So that's how the glyceraldehyde 3-phosphate leaves. This is glyceraldehyde 3-phosphate. It leaves, and now we have this carbon-carbon double bond. Technically, it's an enol. We have, or an enamine, I'm sorry, because we have an alkene with an amine attached to it. And then it's just a reversal. This comes and retact, we remake the shift base. This takes that hydrogen, so now we have the imine. And one thing that they don't show that's just implied is you have a water here that comes in, and that water attacks this carbon twice to pop off both of those bonds. So you get your lysine back, and you get the carbonyl group. So I just wanted to point out the shift base. Shift bases are important. They're used to transfer groups. They're used many times to break carbon-carbon bonds that are next door to it. And they're used for decarboxylation reactions. There's one more I'm missing off the top of my head. Oh, racemization, which that one is similar to transfer groups. So like going from D to L and L to D. We're going to see them over and over again. All right, so now we're up to reaction 5. Reaction 5 is only the D hap. This is why sometimes I draw it this way whenever I'm running it all the way out. So this is reaction 5, whereas this one goes directly on to 6. But remember, from here on, you have to multiply everything by 2. But D hap becomes glyceraldehyde 3-phosphate. What class of enzymes can do this? Like, what's the only difference between D hap and glyceraldehyde 3-phosphate? They have the same number of carbons. They have the same number of oxygens and hydrogens. The only big difference is where it wasn't a ketone, now it's an aldehyde. Like, it literally switched neighboring carbons. What class of enzymes can do that? Or what class or classes of enzymes can do that? It's an isomerase as well. Okay. So number 5 is going to be an isomerase. I took that right out of number 4, which was aldolase. Number 5 is an isomerase. So I put it there, but I'm going to write it out here. Okay, so what class of compounds are these? sugars. They're both sugar-based. How many carbons do they have? So what kind of sugar are they? Triose. And what else do they have in common? Phosphates. And so if we're going to name this one, it would be?
Triosephosphate isomerase.
That's it. So that's why it's not too bad. Triose phosphate isomerase, or TPI, if I was going to abbreviate. Okay, and number 5. It does matter if it's D versus L, only the D enantiomer is recognized, which is pretty common. You know, the enzymes recognize only one-handedness since they are specific. So from here on out, we have to remember we multiply everything by 2. From reaction 6, 7, 8, 9, and 10, you have to multiply everything by 2. So we have 2 glyceraldehyde 3-phosphates. And these 2 glyceraldehyde 3-phosphates are going to become 1,3-bisphosphoglycerate. It's a mouthful. Which, by the way, we've actually seen an enantiomer of this before. Not an enantiomer. We've seen an isomer of the bisphosphate glycerate before. A lot of times they abbreviate this as DPG. Remember, you can have either 1,3-DPG or 2,3-DPG. We actually talked about that with respect to hemoglobin. It's another pathway, that can be wrong. All right. So to point out some of the things that's going on here, we have glyceraldehyde 3-phosphate. Notice we also then have an NAD becoming an NADH, and an inorganic phosphate being added on to make 1,3-bisphosphoglycerate. It's called an oxidative phosphorylation reaction, which is a mouthful. So what are some of the enzymes? I can think of at least 2 classes of enzymes that this would make sense to name it. What's one of them? Phosphorylase. What's the second one? Has to do, what was NAD and NADH? Back. This is the first time I've come across this semester, but I told you we're going to see this a lot. Right, we're talking about this is an oxidation reduction reaction. So what class of enzymes do redox reactions that utilize NAD and NADH? Dehydrogenase, and this is a dehydrogenase. This is a class of enzymes. This is a dehydrogenase.
So we can't name it with phosphorylase at all?
No, it has a phosphorylase reaction. I mean, it's got a property, like I would probably give like partial credit, but the NAD, NADH is what's really important here. Dehydrogenase. So if you're going to name this one, what would we name this one? Glyceraldehyde 3 phosphate dehydrogenase. That's its name. So now we have 1,3-BPG, and this was, I'm going to really abbreviate here because I don't have enough room to write it all out. Okay. So remember, we're multiplying everything by 2. There's a couple things I want to point out. It's very important here. We're going to talk about mechanism some. But this is the first time that we see NADH. What is the whole purpose of ATP? What is the whole purpose of glycolysis?
The amount of energy?
Yeah, we're going to increase the amount of energy. How do we actually increase the amount of energy? Like, what do we, when we say we're going to increase energy, what are we talking about? Like, if we say someone is wealthy, it's because, they have lots of money. So if something has an increase in energy, what will it have more of? So we're going to say on the cellular level, what is the energy currency that's used? ATP. So many times when I say, what's the purpose of glycolysis? And people say make energy, they'll say it's make to ATP. It's only partial true. It's actually not very efficient at making ATP. In fact, so far we haven't made ATP. We've used 2 ATP. Where you get your big bang for your buck is this right here, NADH. This is huge because what you're going to find out later this semester is depending upon which pathway the NADH goes, these are called reducing equivalents, NADH and FADH2 or FMNH2, because they're reduced. They're going to ultimately go on to the electron transport chain. Each one of these typically will go on to make 2.5 molar equivalents of ATP. You get a lot more ATP from NADH than you do directly from, so remember, we've made 2 NADHs already because we have to multiply everything by 2. So those 2 can go on to make, later on, they make 5 ATPs. So that's why the important one is like dehydrogenases. Whenever they make NADHs, those are really, really good because you can utilize that. Well, they'll give up their electrons in the electron transport chain to make even more ATP. We'll find out FADH2 typically makes 1.5. NADH usually makes 2.5. FADH2 makes 1.5. There's a reason why. That's almost always on a quiz or an exam about reason why one makes 1.5, one makes 2.5. We haven't learned that yet, though. This is its mechanism. I just wanted to point out a couple things. Like I said, this is the first time that we've seen NAD and NADH, and so that's why I wanted to show it. Here it's a thiolate. Remember, it's a thiol that's lost its hydrogen, so it becomes negatively charged. So it's a thiolate. And what it does is it just goes, it's actually fairly simple. It smacks that carbon, which is delta plus, to form the tetrahedral intermediate. You get collapse of that tetrahedral intermediate, but this time what's different, and this is where the dehydrogenases are so important. Remember, in organic chemistry, hydrogen's never left with, it was hard to get a hydrogen to leave with its electrons. Because of the environment of the enzyme and the presence of the NAD+, which is so electron deficient, this hydrogen takes the 2 electrons with it. So it actually, notice, it breaks and it takes the electrons with it to make NADH. Okay. Then what happens is an inorganic phosphate comes in to act as a nucleophile, and it just smacks that carbon and pops off the enzyme. So that's why it's not really that difficult. This is to show you how with NAD plus becoming NADH, and the reason why is that hydrogen actually usually takes the electrons with it. All right. Now we're up to reaction 7. Of course, I'm running out of room, so I won't.
What was the star?
Because first of all, remember, you had multiplied 2. The star was because it's the first time that we make NADH. And technically, you're making 2 because you have to multiply everything by 2. And those NADHs are what's really, really important. Okay. Ultimately, so far up to this point, if you read that little introductory pages that I put on MyFire, the first half of this has truly been catabolic process. We broke down, we took something that had 6 carbons, we broke it into 2 parts, to 2 carbons. We actually didn't get any energy out. We had to take up energy. We haven't made any energy. 6 is the first step where you don't directly get energy from it, but later on you get energy as a result of it, if that makes sense. This step 7, one thing that's important about it is this is the first time that we see ATP. So remember, since we're multiplying everything by 2 now, this is where we break even energetically wise. We haven't made an energetic profit yet. Okay.
Oh, because we get those 2 ATPs back.
We got the 2 that we used up earlier, we got them back in this step. So far, the net gain of ATP would be 0 if we stopped at this point, which our body doesn't stop at this point. Right? But if we just look at this, we have 1,3 bisphosphoglycerate becomes 3-phosphoglycerate. You have an ADP that becomes an ATP, so we've got a transfer of phosphate group. So what class of enzyme or enzymes could this be?
Is this one, would it still be a kinase even though it's going to
This is a kinase. Exactly, this is a kinase. I've run out of rooms where you guys will be able to see it anyway. This is a kinase because we are transferring phosphates. Because if it goes backwards, you'd be transferring the phosphate. Okay? And this one is called phosphoglycerate. phosphoglycerate kinase. Those are both of the compounds involved in phosphoglycerate. So that's two. So it's reversible. It does notice it requires magnesium. So that's why in the reverse direction, it makes perfectly logical sense. This is just phosphoglycerate kinase.
But if it, so say this reaction wasn't reversible, would it be still considered a kinase?
Yeah.
Okay.
Okay, now I'm going to go ahead and